everyone. Today we are going to continue the last class discussion, that is general organic chemistry. We are discussing HOMO and LUMO concept. Today we are going to continue that one by considering more and more examples. Let us consider the example in CH3 and OH minus. Which one will be the HOMO and which one will be the LUMO? We all know that the hydroxyl OH minus ion is going to attack the carbocation. Let us know HOMO is highly occupied molecular orbital, which is having high energy and easy donation is there. Easy donation. LUMO means lowest unoccupied molecular orbital, which has low energy, right? Low energy is there and easy acceptance is there. Easily acceptable. Easy acceptance. Right? Last time we have discussed all those things. Easy acceptance is there. In the example of CH3 and OH minus, let us consider how the CH3 will be formed, how the carbocation will be formed during this reaction, right? CH3 and OH minus is there. How the carbocation CH3 is formed means it is formed by CH4 methane molecule. How it is formed means we all know that the electronic configuration of carbon is 1s2, 2s2 and 2p2. Atomic number of carbon is 6. Then it is having electronic configuration, right? Electronic configuration. Right, this is the ground state electronic configuration of carbon, and we all know that it is like this: 1s2 orbital, and this is 2s2 and 2p, 2px1, 2py1, 2pz1 is vacant. But we know that half-filled electronic configuration is more stable than this configuration. Hence, carbon will be there in the form 1s2, 2s1, 2p3. It will be like this: 2s1 and 2px1, 2py1, 2pz1, right? This is the electronic configuration of carbon. Now the 4 hydrogen will be give one electrons to form sigma bond, then only CH4 will be formed, right? Each hydrogen will give 1 electron for 2s orbital and 2px, 2py, 2pz. Then it will be formed like this, right? CH4, which is having tetrahedral structure, sp3 hybridization, 1s and 3p orbitals were involved in the hybridization, so it is having sp3 hybridization, right? Now how the carbocation will form means the H will be eliminated as H minus, right? Then it is having H and H with positive charge. One H will be eliminated as hydride, means it is having in CH3 plus, this is the configuration of CH4, then CH3 plus is having 1s2, 2s2, 2px, 2, 2py, 2 and 2pz is vacant. This is vacant, right? This is p orbital, right? Now in OH molecule, it is in minus charge, right? Oxygen is already having 2 lone pairs of electron, and this is having more electrons. 1 lone pair is extra, hence it is having minus charge. So by considering the right, this is a non-bonding electronic. We can write the electronic configuration of OH minus. This is non-bond. These are non-bonding electrons, right? Non-bonding. Bonding and non-bonding means the electrons which are involved in the formation of bond, right? This is a sigma bond, and these electrons called bonding electrons. Bonding electrons, and these are called as non-bonding electrons. In OH minus, how many pairs are there? 3 lone pairs were there. 3 lone pairs of How they are? They are non-bonding electrons, right? Non-bonding electrons. Now we can write the HOMO and LUMO. We have know that in CH3 plus, in CH3 plus, here bonding molecular orbital is there, and here anti-bonding molecular is there, right? And in between it is non-bonding or p orbital, non-bonding or p orbital, right? In OH also one bonding molecular orbital is there, anti-bonding molecular orbitals were there, and here also non-bonding molecular orbitals were there, right? In CH3 plus, it has sigma bonds, right? It has sigma bond. Number of electrons in sigma bond is 2, right? Sigma star is there, and it is non-bonding electron also there. In OH minus, right? In sigma bond, 2 lone pairs of electrons were there, right? These are 2 lone pairs of electrons, right? In OH minus, 2 lone pairs of electrons were there, and one non-bonding electron pair is there, right? Then from where the electronics were HOMO is nothing but easy donation, right? Where the electrons will be easily donated means from OH minus the electrons were donating easily. Then this non-bonding is become HOMO, right? HOMO of one molecule will reacting with LUMO of another molecule. Then the product will be formed. This is the theory of Frontier Molecular Orbital Theory. Now, from where it will be given, the electrons will, the where electrons are moving means they are moving to vacant p orbital. They are moving to the vacant p orbital of CH3. Then it becomes LUMO, right? Then it becomes LUMO. So the electronic transition is how we can represent the OH non-bonding electrons are shifting towards CH3 carbocation vacant p orbital of vacant p orbital of CH3. Let us consider another example, alkene, right? Alkene means C double bond C, right? Here maybe R is there, H is there, whatever it may be. Here one sigma bond is there, one pi bond is there, right? We can write like this is for sigma, this is for pi, this is for non-bonding, this is for pi star and sigma star. Sigma, pi, non-bonding or p vacant orbital, pi star, sigma star. Here two lone pairs are there in sigma bond, and here two pi electrons are there. So here which one is become HOMO means this is our HOMO and this is our LUMO. In exam they may be asked like this, or previous example we can saw that one. They may also ask like that. Another example for this another example, C double bond O. Here one sigma bond is there and pi bond is there, same like alkene, right? This is sigma and this is pi, and this is non-bonding or p orbital, and this is pi star, and this is sigma star. Here two electrons in sigma bonds were there, and two electrons are there in pi bond, and oxygen is containing two lone pairs of electrons in non-bonding, right? How many electrons were there in non-bonding? Means there are four electrons were there, and we can also say two pairs of electrons were there in non-bonding orbital. It is not orbital, it may be non-bonding electrons were there. Like that we can say, okay, which one is HOMO then? This is HOMO, highest occupied molecular orbital, and this is LUMO, lowest unoccupied molecular orbital. Not sigma star because it is having higher energy. Lowest unoccupied molecular orbital, which is what is the lowest unoccupied molecular orbital here means it is a pi star. Understood? Okay. Another question in alkene and which undergo Br plus, it is forming Br and CH2, 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 right? Which is the Br plus. So which one is HOMO and which one is LUMO? Question is in the reaction, uh, in this reaction, which is HOMO and which one is LUMO? So how to determine this one? In pi, in alkene, one sigma bond is there and one pi bond is there, right? Br is there in Br is there as Br plus, Br plus. Then it is a vacant p orbital. Which one is HOMO then? Highest molecular orbital is pi of alkene to how the electron is how the electrons are going to shift from pi bond to vacant p orbital. So how can we written pi c double bond c to p orbital of Br plus, right? Which one is HOMO? This is HOMO and this is LUMO, right? Let us consider another example in allylic carbocation, that is CH2 double bond CH single bond CH2 plus, which is reacting with OH minus. We have to tell which one is HOMO and LUMO. In this reaction, we have to determine which one is HOMO and which one is LUMO. Here in allylic carbocation, which is having pi, sigma, pi, and non-bonding electrons, pi star and sigma star. Sigma, pi, non-bonding or p orbital, or pi star and sigma star. Right, in sigma, that is filled, two sigma bonds were there and one pi bond is there. Here vacant orbital is there for CH2, similar like CH3, non-bonding p orbital is vacant in OH minus. Sigma non-bonding electrons or p orbitals were there and sigma star. So in sigma, two electrons were there, in non-bonding, two electrons were there. How the electrons are transferred from OH to CH2, CH2 plus, from non-bonding orbital to non-bonding orbital of allylic carbocation, right? In this non-bonding orbital of allylic carbocation, the non-bonding electrons of OH minus will be shift, right? So what is the HOMO? This is the HOMO and this one is the LUMO. HOMO is the non-bonding orbital of OH minus, LUMO is the non-bonding orbital of allylic carbocation. The electron is transferred from non-bonding oxygen OH minus non-bonding orbital to C plus, that is carbocations, non-bonding orbital, right? Or it may be, we can write p orbital. The vacant orbital is p, hence it may be also called as p orbital. So this is the next example in the reaction where the nucleophile will going to attack for this carbocation, or to remove this Br, or to add to this double bond, where the nucleophile is going to attack in this reactant. Means there are three options were there, right? The nucleophile has substituted Br minus, and here nucleophile is attacked to carbocation, and in this reaction the nucleophile is added to double bond and forming primary carbanion. Which one is the correct? So what will be the answer? Means how we have to determine. We all know that in this reactant there are one pi bond is there. Pi means it has empty pi star, right? Pi orbital is there means it has empty pi star orbital, and carbocation is there means it has empty p orbital, right? Empty p orbital, empty p orbital is there. And here Br minus, which is having sigma bond, means it is having sigma star antibonding. It is sigma bond and it is a sigma star antibonding molecular orbital. Let us discuss the energy profile diagram, right? Which is having higher energy. We know that sigma pi molecular orbital in energy profile diagram. It is like this: non-bonding or empty p orbital, and above pi is there, above pi star and sigma star. So the energy order is sigma star is having higher energy than pi star, then non-bonding, or p, then pi, then sigma, right? Nucleophile will attack where the lower energy orbital is there, right? Why it is going to higher energy? It will attack to the orbital which is having lower in energy, right? According to this, where it will attack means it will attack to empty p orbital. Nucleophile will attack to empty p orbital. So, right, or non-bonding electrons. The answer is which is the correct answer? This is the correct answer for this question. This is the correct answer. Like these questions were these questions were asked in the competitive examinations like KSET, GATE. Nucleophile will attack to lower energy orbital, right? Not only another example for this is NMe3 plus BF3, from where the electrons were transferred to which orbital. Similar like HOMO LUMO concept, we have to check we have know that the atomic number of boron is 5, right? Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, like that. Boron is having 5, 1s2, 2s2, 2p1, right? There are two vacant p orbitals, right? There are vacant p orbital. It will be like this, right? For BF3, for BF3, the 2s electron will shift to 2p. So 1s, 2, 2s1, 2p1, 2px, y1. Then one fluorine is giving one electron to 2s1, and that fluorine will give to 2px, and another fluorine will give the electron to 2py, right? Like this, boron is having hybridization with sp2 hybridization is there. Okay, it is having 2pz as vacant, right? 2pz as vacant. BF3 has vacant p orbital, and NMe3 has non-bonding electrons. NMe3, Me means methyl group. Maybe it may be like CH3. They in exam they will give like a CH3. How it will how the electrons are moving from non-bonding orbitals of nitrogen to the vacant p orbital of BF3, right? So then which one is HOMO? The non-bonding electrons of nitrogen will become HOMO, and this is LUMO. How the electrons were shifting? The non-bonding electrons of nitrogen will shift towards the vacant p orbital of boron, right? Like this we have to solve the questions. So in this example, which one is HOMO and which one is LUMO? We have to check which one is HOMO. Here in oxygen, it is already having positive charge, right? In oxygen, it is already having positive charge. Then how to determine? The oxygen is having 3 sigma bonds, and the nitrogen is also having 3 sigma bonds. This sigma bond will cut this sigma bond and this sigma bond. That means I am saying that these two electrons, the bond order is nothing but half of antibonding minus bonding, like that. Here also same bond order is there, here also same bond order is there, but which one is HOMO, which one is LUMO, we have to determine like that. Okay, that's why I have done the cuts, right? Which one is remaining? Oxygen with the positive charge, nitrogen with lone pairs of electrons, right? Case oxygen, non-bonding electrons and This is sigma, this is sigma star, and this is non-bonding. Here also sigma. Why I'm not taking pi means there are no pi bonds. That's what I am leaving that pi, non-bonding, right? So already in oxygen in sigma there are electrons. In sigma bond there are electrons, and non-bonding also they have electrons, right? Non-bonding electrons are having have bonded with hydrogen. Hence it is also filled. The vacant orbital is there in sigma. In nitrogen there are sigma electrons were there and non-bonding electrons were there. How the electrons will shift means, from non-bonding we know that it will abstract the proton, right? Because oxygen is highly electronegative compound and it is satisfied with the two bonding pairs of electron and two non-bonding pairs of electron. Hence the non-bonding electrons of nitrogen will abstract the H plus. H plus is abstracted by how? This is a sigma bond. The electrons must go to the anti-bonding orbital of OH minus. Hence this is the non-bonding, and they will occupy the sigma star anti-bonding of OH, right? Which one is HOMO? This one is HOMO, and this one is LUMO. So how the electrons will going to attack non-bonding of nitrogen to sigma star of OH, right? Non-bonding electrons of nitrogen to sigma star of OH, not oxygen. It will abstract a proton, and then only it will be destabilized, right? This is important. This case is important. This has been asked in NET exam. So the next example is plus HBr. Which one is HOMO and which one is LUMO? In this reaction, we have pi bond, right? We have pi bond. For this sigma pi non-bonding electrons, we will pi star and sigma star. This is sigma star, this is pi star, and this is non-bonding or vacant p orbital. It is a pi, it is sigma. And sigma, there are two electrons were there. In pi also, there were two electrons. There is no non-bonding electrons here. For HBr, H and Br are combined with sigma bond, right? Sigma and sigma star, and this is non-bonding, right? What is the product? What is the product means? The product is CH2 is there, so H and Br. This is the product formed, right? This is the product formed. How that one going to attack means, the pi electrons will shift here in HBr to sigma electrons were there, right? From sigma electrons were there means the vacant orbital is sigma star, not non-bonding. Anti-bonding orbital is that sigma star. Hence the pi orbitals of alkene will occupying the anti-bonding sigma anti-bonding of HBr. How the electrons were moving from pi of C double bond C to sigma star of HBr, right? Correct? Okay. So let us consider this example. We have non-bonding electrons of phosphorus that will attack the carbon. It is like this CH3I. PPH3 is there, which will attack, and I minus will eliminate it. So how the electrons were transferring non-bonding electrons of phosphorus to sigma star of CH3I, right? This one is HOMO, this one is LUMO. In next example, so how the NH4 plus and OH minus we are going to attack means, the OH minus will abstract the H plus. Here the non-bonding electrons of oxygen are shifting towards sigma star of NH, right? The non-bonding electrons of oxygen becomes HOMO, and this one is LUMO, right? Now I think the FMO has been cleared. In next class we can discuss another topics of general organic chemistry like carbocation, carbanion, bond energy, S character, P character, electronegativity, all those things.